So thanks everyone for coming. I'm Ashwin, a staff engineer at IBM. First, let's take a step back. Why are we even running Kafka on Kubernetes in the first place? And to answer this, let's rewind a bit. A few years ago, running Kafka meant setting up dedicated virtual machine or even bare metal servers. Managing them was complex, scaling required manual intervention, and deployments were slow. Then came the cloud, things got easier. But still running Kafka at scale requires significant operational expertise. Now, enter Kubernetes, the ultimate abstraction layer for deploying and managing distributed system and containerized software. Kubernetes makes it easy to scale Kafka dynamically, automate failover, optimize resource utilization across environments. No more manually provisioning brokers or no more worrying about hardware constraints, just declarative configuration and automated orchestration. Sounds perfect, right? Now, Kubernetes itself is great, but running Kafka on Kubernetes isn't just about deploying a bunch of pods. Kafka is a stateful system. It needs persistent storage, coordinated scaling, careful redirection, and controlled rolling updates. That's where Kubernetes operator come in. Now, think of an operator as your Kafka side reliability engineer, but in software form. It continuously monitors your Kafka deployments, ensure brokers stay healthy, automate scaling, and manages configuration. All right. So, running Kafka across multiple Kubernetes clusters seems like a great idea. But it's not as simple as just running more brokers in different Kubernetes clusters. There are some serious challenges we need to address. The important challenge is networking. So what happens if a Kubernetes cluster goes down? Let's see. So Kubernetes clusters are isolated by default. Running Kafka across multiple Kubernetes Kubernetes clusters are isolated by default. Running Kafka across multiple Kubernetes cluster needs to run like, we need to ensure that all ports are distributed and it works seamlessly. The next challenge is metadata and state synchronization. In a multi-cluster Kafka setup, all brokers share the same metadata, topic partition, leadership information, and cluster state. But when brokers are spread across multiple Kubernetes clusters, keeping them in sync without introducing excessive replication lag is tricky. Then there's fault tolerance and failover. We need to, if one Kubernetes cluster goes down, how do we ensure Kafka continues running smoothly without interruption of split brain scenario? And finally, security and authentication. How do we ensure secure cross-cluster communication without introducing excessive replication lag? Now, how do we approach this? One traditional approach is using Mirror Maker or similar replication tool. But since Kafka expects all nodes to communicate seamlessly, what we need to do is like a Mirror Maker introduce latency and operational overhead. So instead of solving the issue with Mirror Maker, what we need to do is we need to look for an operator-driven approach. StreamC, the open source operator for Kafka, is a great foundation for this. It has two key features, which is Kafka Node Pool and StreamC Port Set. Kafka Node Pool is a relatively new abstraction in StreamC that allows us to define group of Kafka nodes independently. It abstracts away the complexity and allows you to define your Kafka cluster declaratively, meaning you specify what you want and the operator take care of the how. No more manually restarting broker or worrying about uneven partition distribution. Now, Kafka Node Pool, as I mentioned, is a new feature, and StreamC Port Set is what controls deployment of ports within a Kubernetes cluster. So StreamC Port Set allows us to define group of Kafka ports and manages it in a Kubernetes cluster. So with Kafka Node Pool defining the port placement and StreamC Port Set handling the deployment, we can distribute Kafka brokers and controllers across multiple Kubernetes clusters while treating them as a single logical cluster. But we need to solve a few key problems. Like, as I mentioned, these are the few key problems like networking, state synchronization, fault tolerance, and failover. Kubernetes cluster, as I mentioned before, is isolated. And it's not about just running more brokers in different Kubernetes clusters. There are some other serious challenges like synchronization, fault tolerance, and security. So moving on, we need to ensure networking works fine as well. And security is one of the critical aspects. So in a multi-cluster Kafka deployment, we encrypt all cross-cluster traffic and enforce strict RBAC policies and securely store remote cluster credential as kubeconfig and environment variable in the central cluster operator deployment. And how do we do this? We use two cross-cluster networking technologies for this, Submariner and Cilium. Submariner establishes secure cross-cluster communication. It enables Kafka port to communicate without complex networking hacks. And Cilium provides eBPF-based networking, ensuring better security, visibility, and control over how data moves between clusters. So once Kubernetes clusters are connected to each other using one of these technologies, we need to make sure Kafka itself understands the setup. That's where two key configurations come into play: controller quorum voters and advertised listeners. Controller quorum voters control which node participate in lead election. Instead of keeping all the controller code in one Kubernetes cluster, we distribute it across multiple Kubernetes clusters, ensuring seamless failover if a cluster goes down. And the next property is the advertised listener. Advertised listeners define how brokers and clients find each other. In a multi-cluster Kafka setup, we dynamically configure this to use Submariner and Cilium Explore service name, ensuring cross-cluster communication happens smoothly. And of course, security is critical. We encrypt all cross-cluster traffic, enforce strict RBAC policies, and securely store remote cluster credential as kubeconfig environment variable in the central cluster operator deployment. With this, we get a multi-cluster Kafka deployment, which is highly available, scalable, and fault-tolerant, without requiring complex manual configuration. Now, let me try to explain the high-level architecture of a multi-cluster Kafka deployment. Here you can see 3 Kubernetes clusters. For the simplicity, I've shown 3, but in reality, or in theory, you can have any number, ideally an odd number, to maintain quorum in case of a cluster failure. From a user perspective, all they need to do is apply Kafka and Kafka Node Pool CRs in one of these Kubernetes clusters. Now, all these clusters should be automatically connected using one of the cross-cluster communication technology which I've described before, like Submariner or Cilium. In addition to applying this here, user just need to set a couple of environment variables in the central cluster operator deployment. And it is to make sure that operator is aware that we are running Kafka across multiple Kubernetes clusters. At this point, the operator in the central cluster will take over. It dynamically generates controller quorum voters and advertised listener, and also it will spread Kafka broker and controller port across Kubernetes clusters to establish secure cross-cluster communication. User doesn't need to worry about any of the behind-the-scene operations. The cluster operator in the remote cluster is responsible for reconciling the StreamC port set CRs to ensure that everything runs smoothly. Now, a common question is, what happens if the primary cluster fails? That's a great question. The key design principle is that we are not relying on a single central cluster. Instead, we distribute leadership across multiple Kubernetes clusters, enabling seamless failover if a cluster goes down. Now, in a standard StreamC deployment, controller quorum voters and advertised listeners are automatically generated based on the detected broker configuration. By default, StreamC assumes all ports reside within a single Kubernetes cluster. So it uses internal service DNS name for communication. Now, in a multi-cluster Kafka deployment, ports are spread across multiple Kubernetes clusters. So keeping them in sync without introducing excessive replication lag is a bit tricky. So the idea is to use the technologies like Submariner and Cilium to establish a direct port-to-port communication so that there is no need to introduce additional latency. So these tools are well tested, and it works really well when it comes to communication across Kubernetes clusters. Now we have tested these technologies using Open Messaging Benchmark, a framework used for testing performance of distributed data systems. And the results were promising with minimal overhead. Now, what happens is that these technologies provides a truly resilient multi-cluster Kafka deployment with minimal overhead for the user. And by that, what we mean is that we can have a multi-cluster Kafka deployment that is spread across clusters without treating them as a single logical deployment. So we have a multi-cluster deployment which is a single logical Kafka deployment. Now, there are some key benefits of this, like multi-cluster Kafka enables high resilience and high availability. If you leverage Kubernetes on StreamC, it will enable automation and scalability, and it is cloud native. It solves the issue of cross-cluster communication. And in future, we are aiming for more optimization and improved failure and latency. So these things are still in proposal stage in the StreamC community, and we are hoping to get an approval pretty soon. So this isn't just about solving a single problem. Instead, we push the boundaries of what's possible with Kafka on Kubernetes. As the ecosystem evolves, ideas like this will shape the future of distributed data systems. Yep, that's pretty much it. I wanted to talk and open for questions.
Hi, this is Sandeep. One question, when the primary cluster goes down, how does the producer or consumer application connect to the other cluster?
See, we are not relying on a single central cluster. Actually, we distribute leadership across multiple Kubernetes clusters. So even if the primary cluster goes down, client will still be able to get connected to the remaining Kubernetes cluster, and everything works normally. Nothing will happen again. It will still be functional.
So, but there will be change in the brokers, right? The broker configurations.
Sorry?
The application has to connect to.
Yeah. So the way StreamC works is it has, if you are connecting from external systems, right, there is a bootstrap address, external bootstrap address which you can use. So all the different Kubernetes cluster will expose external bootstrap addresses. So if one cluster goes down, client will automatically fall to the next bootstrap address, and connection will work without any interruption.
Okay.
Yeah.
What was the primary reason for you to consider using like Kafka on like deploying your own brokers and all versus using MSK or?
Yeah, sure, definitely. I'll come to that. So the thing is, many businesses are in fully cloud native yet, right? So industries like finance, healthcare, and telecom often have strict regulations around data sovereignty and compliance, requiring them to keep certain workload on premises. So multi-cluster Kafka in on-prem or hybrid mode just provide that.
As we are running Kafka in multiple clusters, so there is a chance for multiple controllers as well. How are we handling the split brain situation?
Sorry?
Split brain.
Yeah, split brain scenarios, yes. Actually, yeah, split brain scenarios won't be an issue here. Why? Because, leadership is automatically distributed, and the data will be already replicated across all the, brokers or controllers out there. So even if one cluster goes down, the data will be already there in other brokers. So there won't be an issue of split brain scenarios in this case, yeah.
Okay, will there be multiple controllers or one controller?
No, there will be multiple controllers, and all the controllers will be spread across multiple Kubernetes clusters. So if you have 3 clusters, all the 3 clusters will have its own controllers.
Okay.
How much is the cost impact, like higher, lower?
Cost, I'm not able to disclose this at the moment, but it should be in a medium range. I'm not really sure, but we have the product management here. If you want to discuss more about the cost line, I'll get you connected with them, one of those peoples.
We are at time, but please find Ashwin later to ask more questions. And thank you, Ashwin, for this amazing presentation. I definitely learned something new. Big applause to Ashwin. Thank you.